Hello everyone, this is Rashaka Janjarla. I am an educator at Unacademy. You can follow me on Unacademy Learning Hub where you can find mother course as well. In this lecture, we are going to discuss about the mechanical springs. Here in this cutter, you can find a torsional spring which is useful for providing the restoring torque for the comfortable use of this cutter. Okay, so please rate, review and share the video and also subscribe to Unacademy YouTube channel. Welcome again to mechanical springs. The flexibility is sometimes needed and is often provided by metal bodies with the cleverly controlled geometry. We call these metal bodies as springs and they have different geometries and we call them as the types of springs. Okay, these bodies can exhibit flexibility to the degree the designer seeks. Such flexibility can be linear or non-linear in relating the deflection to load. So we can have the desired values of the flexibility depending upon the geometry of the springs used. Okay, these devices allow controlled applications of force or torque. The storing and release of energy can be another purpose. These springs stores the energy and they release the energy according to our requirement. Flexibility allows temporary distortion for access and the immediate restoration of the function. Okay, so these flexibility is provided from the mechanical elements called the springs. In this chapter, we will discuss the more frequently used types of springs, their necessary parametric relationships and their design. So here we have the types of springs. In general, springs may be classified as wire springs, flat springs or special shaped springs, and there are variations within these divisions. Okay, so wire springs include helical springs of round or square wire made to resist and deflect under tensile, compressive or torsion loads. Here in this figure you can find helical compression springs and the helical extension springs, conical springs and the torsion spring. As you can see in these figures, you have found these springs are made from the wire, right? That's why we call these springs as wire springs. They include helical springs, this one and the conical springs and also the torsion springs. They are made to resist the deflection under tensile, compressive and torsion loads. So the torsion springs resist the torsion loads and this one compressive loads and this one is extension loads or the tensile loads and this is also for the compression loads. Okay, so the flat springs include cantilever and elliptic types, wound motor or clock type power springs and the flat springs washers usually called bellwell springs. So these are the bellwell springs which are included in the flat spring category. So and here we have the leaf springs which are also included in the flat spring category. Okay, so depending upon our requirement, our purpose, we select the type of springs. Okay, if we want to resist the compression, we have to use helical compression springs. If we want to resist the extension, we have to use the helical extension springs, and if we have to resist the torsional loading on any mechanical element, we have to use the torsional springs. So the terminology of helical springs. So the main purpose of this discussion is about the helical springs which are used in most mechanical applications. They resist the compressive loads. You can see these helical springs everywhere in various applications. Okay, so the main dimensions of the helical spring subjected to various compressive forces are shown in this figure. You can find we have a typical helical spring and the dimensions are provided in this figure. Their dimensions are d equals to y diameter of the spring. See here we have the wire. As I said before, these helical springs are included in the wire springs, right? That's why they are made of wires and mostly we use the round wires. As you can see in this figure, they are made from the wire, right? As you can see, the cross section is a circle. That's why these are the round springs and the diameter here is the wire diameter, the diameter of the wire used for the spring, and di is the inside diameter of the spring coil. So see here, this is the inside diameter of the spring coil, which is the distance between this circle and this circle, starting of these two circles as shown in this figure, and d node is the outside diameter of the spring coil. Okay, and d, the mean coil diameter, is given by di plus d node by 2, where it is di is the inside diameter of the springs and d node is the outside diameter of the spring. Okay, so this is the mean coil diameter which is given here in this figure, which is the distance between the centers of these two wires, right? And the spring index, it is defined as the ratio of mean coil diameter to wire diameter, okay, which is given by C equal to D by T. This is very important parameter. We are going to use this parameter in deriving the stresses, stress relations, and also everything about helical stresses, okay, helical springs. So three other terms are here for the terminology: free length, compressed length, and the solid length. Here we have free length. Free length is defined as the axial length of an unloaded helical compression spring. So see here, we have a spring. When there is no loading on the spring, the length measured to be equals to the free length of the spring, okay. So see here, this is the free length, and the free length is given by solid length plus total axial gap plus delta. So solid length is defined as this, which when you compress the spring, as much as the adjacent coils of the springs are touch each other. So here in this figure you can see each adjacent coil of this spring are touching each other, right? So this length is called as the solid length of the spring, okay. And the total axial gap is the distance between, so when it is under any load, the distance measured is given by axial gap. So okay, so total axial gap will gives us the distance between the two adjacent coils when it is under some maximum load given by P maximum here, and delta is the deflection cost in the spring when we apply some load, okay. So the pitch of the coil is the axial distance between the adjacent coils in uncompressed state of springs. So while we are measuring the free length, the spring is in uncompressed state, right, or in free state, right? That's why we can measure the pitch of the coil as the distance between the adjacent coils, okay. So the distance between these two coils will give us the pitch, and any two adjacent coils will give us the pitch of the coil. And P is given by free length by Nt minus 1, where Nt is the total number of coils. Remember all these formulas in our coming explanations or in coming lectures. You better have the knowledge about these terms, okay. Stiffness of the springs is the force required to produce unit deflection. Therefore it is given by K equals to P by delta. So if we apply some amount of force which causes the unit deflection, therefore that value is given by K, it is equals to P by delta. Here we have compression length. Compressed length is defined as the axial length of the spring which is subjected to maximum compressive force. So if we apply maximum compressive force on the helical spring, the length of the spring is called as the compressed length of the spring, okay. The total gap is given by Nt minus 1 into gap between adjacent coils. So see here, after compressing this spring, there will be some distance between the adjacent coils, right? The total gap, which means sum of the gaps between the adjacent coils of this spring, is given by Nt minus 1 into gap between adjacent coils. It means the individual gap, the gap between two adjacent coils gives us the value G gap, and Nt minus 1 is the number of coils, right? Number of active coils. So the total gaps will be the distance between two adjacent coils and also the number of active coils in that springs. And also the solid length, it is defined as the axial length of the spring which is so compressed that the adjacent coils touch each other, okay. See here, in this state the length measured to be equals to the solid length. As I said before, the solid length is given by Nt into D, where Nt is the number of springs and coils in the spring, and D is the diameter of the wire used for the development of this spring, okay. Thank you.